Hello friends, I welcome you on my channel Engineering Mathematics DJ Ganit. So today we are going to discuss about inverse trigonometric functions of complex variables. So we start with the definition and then we will prove some identities involving inverse trigonometric functions. So the definition is in this way. If we have sin w equal to z, then this w is called inverse of this function sin z. So the inverse sin w equal to sin inverse z is the relation such that sin w equal to z. So this is the way how we define. If sin w equal to z, then w is nothing but sin inverse of z. Similarly, the inverse cosine w equal to cos inverse z is the relation such that cos w equal to z. And we can define other inverse trigonometric functions like tan, cot, sec, cosec in a similar fashion. So we will just remember this that if cos w is z, then w is nothing but inverse cosine of z. So we have some formulas for this inverse trigonometric functions. So we try to prove that formulas. So these formulas are in terms of logarithmic function. So we know a complex logarithmic function. So using that logarithmic function, we are able to represent inverse trigonometric functions in terms of logarithmic functions. So first we prove this. Cos inverse z is nothing but minus I log of z plus I times square root of 1 minus z square. So we start by assuming that cos inverse z is say w. Then by definition cos w must be equal to z. Now here we use the definition of cos w. So by definition cos w is e raised to iw plus e raised to minus iw over 2 equal to z. Now in the next step we take these 2 on right hand side. So we have e raised to iw plus e raised to minus iw equal to 2z. Then we multiply this equation by e raised to iw. So e raised to iw square, if we multiply this e raised to minus iw with e raised to iw, we have e raised to 0, that is 1, and 2z times e raised to iw. And then we transfer this term on left hand side and we obtain this quadratic equation in variable e raised to iw. So e raised to iw square minus 2z e raised to iw plus 1 equal to 0. So this is nothing but quadratic equation in variable e raised to iw. So the solution of this quadratic equation is given by e raised to iw equal to minus coefficient of e raised to iw, which is minus 2z, plus or minus square of coefficient of e raised to iw, which is minus 2z square, minus 4 times coefficient of e raised to iw square, which is 1, and the constant term, which is 1, over 2 times coefficient of e raised to iw square, which is 1. So if we simplify, we have e raised to iw equal to 2z plus or minus square root of 4z square minus 4 divided by 2. Here we have 4 in both the terms. So if we take 4 common, we will have square root of 4 times z square minus 1, and square root of 4 is 2, that we have written here directly. So 2 is there in both the terms, so that can be taken common and that will cancel out with this 2. So we have e raised to iw equal to z plus square root of z square minus 1. Here in this step I have not written plus or minus, because we know that z square minus 1 is double valued function, so it always has two possible values, so it is not used here plus or minus. Instead of plus or minus we can write only positive sign also, because this function is also having two values, so it is double valued function. Now in the formula we require square root of 1 minus z square, and here we obtain square root of z square minus 1. So we rewrite this as minus 1 minus z square, that is minus 1 times, we rewrite this as minus 1 times 1 minus z square, because we require square root of 1 minus z square in the formula. And then we replace this minus 1 by I square, and square root of I square is I, so we obtain e raised to iw equal to z plus I times square root of 1 minus z square. Now we have to use the definition of logarithmic function. So we know that if e raised to w is z, then w is nothing but log of right hand side, which is z. So here we have e raised to iw and right hand side is this expression. So using the definition of logarithmic function, we obtain iw equal to log of z plus I times square root of 1 minus z square. So this is by definition of logarithmic function. Now we transfer this I on left hand side, so we have 1 over I log of z plus I under root 1 minus z square, and 1 upon I is nothing but minus I, and w is cos inverse z. So we are able to prove that cos inverse z is minus I times log of z plus I into under root 1 minus z square. So this formula is useful in solving this type of equations. Suppose I have cos z equal to 2. Then using this formula I can solve this equation like this, z equal to cos inverse 2. So here I can put z equal to 2 and I can find out this value. So this is very useful formula. Next formula we have shown for tan inverse z. For sin inverse z, this formula can be derived using the same process as we did for cos inverse z. So I have not derived the formula for sin inverse z, but the method for deriving the formula for sin inverse z is similar to this one. Instead of cos, we have to replace cos by sin, and we are able to prove the formula for sin inverse z in this similar way. So now we try to prove the formula for inverse trigonometric function tan inverse z. So tan inverse z can be proved to be equal to I over 2 log of I plus z upon I minus z. So we start by taking tan inverse z equal to w. So therefore by definition we obtain tan w equal to z. Now we use the definition of tan w. Tan w is sin w over cos w, which is equal to z. Now by definition sin w is e raised to iw minus e raised to minus iw over 2i divided by cos w, which is e raised to iw plus e raised to minus iw divided by 2, which is equal to z. So here 1 by 2 will cancel out and we are left with e raised to iw minus e raised to minus iw divided by I times e raised to iw plus e raised to minus iw equal to z. So now I consider in the next step I replace this 1 upon I by minus I. So I obtain z equal to minus I times this expression. Now in the formula we require I plus z upon I minus z. So first we find out I over z. So I transfer this z on right hand side, so I will have I over z, and I transfer this expression on left hand side, so that will be e raised to iw plus e raised to minus iw, and I multiply this negative sign with this one, so I will have e raised to minus iw, that will be positive. If I multiply this term by negative sign, I will have e raised to minus iw minus e raised to iw. Now I require I plus z upon I minus z, so I use the compoundando dividendo rule, and I consider I plus z upon I minus z, that is numerator plus denominator divided by numerator minus denominator. So first here also we add these two. If we add these two, we can see e raised to iw will cancel out, and we will have 2 times e raised to minus iw divided by, now we have to subtract this denominator from numerator. So if we subtract this denominator from numerator, you can see e raised to minus iw will cancel out, and we will have 2 times e raised to iw. So here 2 will cancel out, and if we take e raised to minus iw equal to 1 upon e raised to iw, we have 1 upon e raised to 2iw. Now this 1 upon e raised to 2iw can be rewritten as e raised to minus 2iw, so that is equal to I plus z upon I minus z. Now again we use the definition of log z, so from this we can write minus 2iw equal to log of right hand side, which is log of I plus z upon I minus z, and then I take this minus 2i on right hand side, so I have w equal to minus 1 upon 2i log of I plus z upon I minus z. Now if I write minus 1 equal to I square, 1 I will cancel out, and I will obtain I by 2 and log of I plus z upon I minus z, and w is nothing but tan inverse z. So we are able to prove that tan inverse z equal to I by 2 log of I plus z upon I minus z. So this is all about today's session. We have defined inverse trigonometric functions, and we have proved the formulas for cos inverse z and tan inverse z in terms of logarithmic function. Similarly, you can derive the formulas for remaining inverse trigonometric functions. So I hope you like this lecture. Thank you very much.